from the bottom of a triangle. So we're going to put here a resultant with a double hash, and that resultant now will be equal to the area under this curve, which is 10 times 624, right? It was 6240, but a half of that, so it's 3120 pounds. So you have a vector which is force of 3120 pounds here. You have two unknown vectors here, which is actually just the contact force of the hinge, and then you have an unknown force at the reaction at B in the x direction. This is what you should be able to solve now just by looking at it to determine this, because force times distance equals force times distance. This problem here is something that you should be able to look at and say, boy, this is just a lever problem, and is this going to be more or less? It's going to be less because it's farther away. It's a ratio of 10 to 2/3 10, right? 2/3, so it's actually going to be 2/3 of 3120. That's what you should be able to do. Force times distance equals force times distance. However, our goal here now is to apply vector algebra to this. And so what I'm going to do right now is going to erase it all off. We're just going to put the pure vector. And what you'll see when we lay out that vector is we're going to do some transmitting vectors along, and we're not going to show this pressure distribution, even though we always want to put it back once we solve for the reactions. So I'm going to go ahead and erase this out. And again, we'll try over and over again to use different media. I'll put this kind of general problem back up. Remember, it was 10 foot tall, and it had a gate here, and you had a flat valve there. Now let's look at what the free body diagram looks like if we start thinking in X, Y, and Z. Well, the free body diagram, we have this here and here. We call that our origin. We have a known force, which we've calculated, that looks like this, which is equal to 3120, but what we're going to try to do is think about vectors having a magnitude, a direction, and a point of application. And so actually what you see that means, each vector has a line of action, but what we're going to do is we're going to slide that vector, which is equal to 3120, along that line of action, still give it the double hash, put that as 3120. In reality, that was just some algebra that led to that. It was what? 10 times gamma times 10 divided by 2, the area under the triangle. We now have also a vector here, which is the force of reaction at B in the x. Again, we continue to show it positive. We're showing this is positive and this is positive. We're going to write our sum of the moments about that point, which means we have to know what a moment is at this point. So we have to know that a moment is equal to R cross F. And that means R is going to be the radial vector from the point of spin, and F is going to be the vector that is the force. This also equals to R, the magnitude of R, times the magnitude of F, times what? Well, I'm going to tell you what that vector is going to be, the vector of the deflection angle where you walk down R and turn towards F. However, that is also, you're going to find out, it is the direction of F. So we're going to write now, it's the magnitude of R times the magnitude of F times the sine of theta sub F minus theta sub R. In other words, this is the deflection angle. You've looked at it in other classes. You'll see this again, that the definition of the moment of any force is going to be the R cross F. We're going to do it vectorially in a little bit. It is also the magnitude of the radial vector times the magnitude of the force vector times the sine of the force direction minus the radial direction. And we can come back and feed these in when we need to. That's going to be true for this force. It's also going to be true for this force. And we know that the sum of all these moments has to be equal to 0. So now let's define our vectors. All right. Well, for this one, the hydrostatic vector, the radial vector is equal to, well, let's think about it. Here's our coordinate system. It goes down z. It doesn't have a change in x, and it doesn't have a change in y. So it's 0I plus 0j. And now it's what? 2/3 of 10. That's 20/3. So I'll just make it 20/3. But it's a negative. So I'm going to put plus minus 20/3 k. Why is it k? It's not. Yes, it is. It goes down here. That is this vector from here to here. It's the vector from the spinning point to the point of application of the force. What is the force vector? The force vector is equal to 3120 in the x direction plus 0 in the y direction, j, plus 0 in the k direction. This here are the radial vector and the force vector for the hydrostatic force. Now, we'll write this out. We do not know what this value is, but we know that it is an unknown magnitude times a known direction in this case. So we can write out the other radial vector. Radial vector to, or to b, is equal to, well, 0I plus 0j plus a minus 10 times k. In other words, it's 10 from here to here. You're fixing your finger on the spinning point and drawing all the radial vectors from there. The next thing is you need to know that force, which you don't know what it's equal to, but you do know that it's some unknown x times I plus 0 in the j plus 0 in the k. The reason why you keep these zeros up here is that you're going to like to grab and write some vectors here, right? And some cross products, perhaps using a spreadsheet, perhaps using paper, but you need to know that your vectors, that the moment is defined as the radial vector cross product with the force vector. And those vectors have magnitude and direction and point of application. The point of application determines what's your radial vector here. In this case, you notice we have transmitted our 0, 0 point on our coordinate system up to here, so we can do some really easy math on our radial vectors. Though you could see we could have just done radial vectors and subtracted them out. Look back at some basic stuff out of Wikipedia about how you add and subtract vectors. Look back at some physics stuff. But realize what all we're really doing is doing force times distance here. This problem is a problem we do because it's straightforward, and you should be able to kind of go to a point and realize it's force times distance equals force times distance. It's going to be less than 3120, but eventually you can solve this vectorially. So let me go ahead and erase off a little bit more. And I will leave this up. I will erase out the vector because now it's all thought out, and I'm going to write out the moment of the hydrostatic force is equal to, well, it's determined. IJK 0, 0 minus 20/3, 3120 pounds, 0, 0. It's that determinant. So this, the determinant of this, is the moment of the hydrostatic force pushing this way, double hatch. It is positive because it's turning my thumb out of the board in the direction we have. We know that the moment of the reaction force at B is going to be also equal to R cross F, and that's going to be IJK 0, 0 minus 10, x as a variable unknown, 0 and 0, and you know that this plus this must be equal to 0. This gets you a bunch of i's, a bunch of j's. No, it gets you only j's. And why is that? Because if this is spinning, it's going to come out in this direction, and this is my j direction or my y direction. This one here will also only get you j's. And so you'll end up with this plus this equals 0.